reality is broken. Not metaphorically, literally broken. At the smallest scale, things don't follow rules. They don't follow logic. They don't even follow common sense. The worst part? N. The math works perfectly. The predictions are right every single time. We just have no idea what it means. Welcome to quantum mechanics. The place where physics stopped making sense and somehow became the most successful theory in human history. And trust me, we are about to dive into some absolute madness that will make you question if reality itself is just a simulation. If you want to make sure you never miss a trip down the rabbit hole like this, go ahead and subscribe. Okay, so here's the thing. You've probably heard the word quantum thrown around a lot. Quantum this, quantum that, quantum healing, quantum coffee. At this point, the word has been so abused that it's basically meaningless in pop culture. But in actual physics, it means something extremely specific. And understanding what it actually means is going to change how you see the entire universe. So let's start at the very beginning. The most embarrassing moment in the history of classical physics. It's the year 1900. Scientists have figured out basically everything. Gravity? N. Done. Electricity? N. Done. Magnetism? N. Done. Light? N. Done-ish. Thermodynamics? N. Absolutely cooked. Like chef's kiss, done. The general vibe among physicists at the time was basically, we've figured out nature, we just need to clean up a few loose ends. One physicist literally said, the future of physics was just about adding more decimal places to existing measurements. That physicist did not have a good century. Because two of those loose ends, they weren't loose ends. They were the entire universe telling us we'd been wrong about everything. The first loose end was something called blackbody radiation. Here's what that is. Heat up a piece of metal. It glows. First red, then orange, then white hot. Scientists in 1900 could describe this. But when they tried to predict it mathematically using the rules they already had, the equations literally exploded to infinity. The energy at high frequencies should have been infinite, which is insane. This became known as the ultraviolet catastrophe, which sounds like either a physics crisis or a really bad 2000s punk band name. Both, honestly. And then a guy named Max Planck did something weird. Kind of desperate, honestly. He said, okay, what if energy doesn't flow in a smooth continuous stream? N. What if it only comes in discrete little chunks? N. Little packets? N. He called them quanta, from the Latin word for how much. He didn't really believe it. He thought he was doing a math trick. But it worked. The equations stopped exploding. The predictions matched reality perfectly. Wait, hold on. If energy only comes in chunks, that means reality at the smallest level is chunky? Like, not smooth? Like pixels on a screen? Wow. Exactly like that, actually. And that one weird fix from one desperate physicist in 1900 was the crack that eventually split classical physics in half. 5 years later, Einstein used the same idea to explain a completely different puzzle. The photoelectric effect. And here's what was weird about it. Shine a light on metal and it knocks electrons loose. Fine. But here's the thing. Dim light, no matter how long you shine it, knocks out 0 electrons. But bright light, even for a fraction of a second, knocks them out instantly. The intensity didn't matter. Only the frequency. The color of light. Why? N. Einstein said light isn't a wave. Not exactly. It's also particles. Little packets of energy. Photons. The frequency tells you how much energy each photon has. Dim light means fewer photons. High frequency light means each photon packs enough punch to knock an electron loose. Low-frequency light means each photon is weak sauce, no matter how many of them you throw. Einstein won the Nobel Prize for this. Not for relativity. For this. The photoelectric effect. Which, every time I say that, sounds like I'm making it up. But it's true. Now, here's where things get genuinely weird. Because if light is both a wave and a particle, what even is light? What does it mean to be both? N. And if light can be both, can other stuff be both too? N? Oh, buddy. You have no idea what's coming. So let's talk about electrons. Tiny little things. Way smaller than atoms. The stuff that makes electricity work, makes chemistry work, makes your phone work. For a while, scientists thought they were just tiny balls of charge zipping around the nucleus of an atom, like little planets orbiting a sun. Nice. Clean. Logical. Wrong. In 1924, a French physics student named Louis de Broglie, and yes, it's pronounced de Broglie. French people are just built different, proposed something absolutely unhinged in his doctoral thesis. He said if light can be both a wave and a particle, maybe electrons can too. Maybe everything has a wavelength. His thesis committee reportedly didn't know what to do with it. They literally wrote to Einstein and asked, "Is this guy a genius or is he cooked?" N. Einstein said genius. De Broglie got his PhD, later got the Nobel Prize, and then someone actually tested it. The Double-Slit Experiment. This is it. This is the one. If you only remember one thing from this video, remember this. Take a wall. Put two thin slits in it. Shoot electrons at the wall one at a time. On the other side, you've got a detector screen that records where each electron lands. Now, if electrons were just little balls, what would you expect? Two lines on the screen, right? And one for each slit. Like throwing tennis balls through two gaps. You'd get two piles. That is not what happens. Wah. You get an interference pattern. Dozens of alternating bands. Like waves overlapping. Like when you drop two stones in a pond and the ripples cross each other, some waves add up, some cancel out. The electron, one electron, fired alone, with no other electrons around to interfere with, goes through both slits at the same time and interferes with itself. When no one is watching, the electron literally acts like a wave spread through space. It exists as a smear of probability across both slits simultaneously. But here's where your brain breaks. If you put a detector at the slits, if you try to catch the electron going through, trying to find out which slit it actually used, the interference pattern disappears. You get two lines. The electron suddenly behaves like a particle again. Like it knew you were watching. Like it changed its behavior because you looked. The act of measurement changes the result. Not because your equipment is clunky. Not because you accidentally nudged the electron. But fundamentally, at the deepest level of reality, observation and reality are not separate things. They are connected in a way that has no classical parallel whatsoever. This is not philosophy. This is not metaphor. This is the experimental result. It has been confirmed thousands of times with electrons, photons, atoms, molecules. Even molecules made of 60 carbon atoms, a thing literally visible under a microscope, have shown interference patterns. Reality at the quantum level does not commit to being in a specific state until it has to. This is superposition. And okay, before you groan and say, this sounds like the Schrödinger's cat thing, yes, exactly. That's the whole point of Schrödinger's cat. And it wasn't meant to be cute. Erwin Schrödinger was actually annoyed. He came up with the cat as a reductio ad absurdum. A joke. A protest. He was basically saying, look how ridiculous quantum mechanics is. If superposition is real, then you could have a cat that is simultaneously alive and dead until you look in the box. He meant it as a criticism. He was trying to show that something was wrong with quantum theory. And then everyone put the cat on t-shirts. And apparently we're all fine with it now. But Schrödinger's frustration was pointing at something real. The question of what superposition actually means, whether the electron is really in both places, or whether it's just that we don't know which place it's in until we look, is one of the deepest unresolved questions in all of physics. We'll come back to that. First, the midpoint. Stop everything. Because here's the thing that genuinely breaks me every time I think about it. Wah! The double-slit experiment has been done with a delay. After the electron passes through the slits, after it has already landed on the screen, scientists have gone back and retroactively decided whether to measure which slit it used. And the pattern on the screen changed, based on a decision made after the electron already hit. It is called the delayed choice experiment. It was proposed by John Wheeler in 1978. It has been confirmed experimentally. It suggests, and physicists genuinely argue about what to make of this, that the electron's past behavior, which slit it, went through, is not fixed until a measurement is made in the present. Not that we don't know it. That it genuinely didn't happen yet. The present can reach back and affect the past. At the quantum level, right now, this is not a metaphor. Take a second with that. Okay, so we've established that particles can be in two states at once, that observation collapses those states into one, and that the past might not be fixed until it's observed. Any reasonable person at this point would say, so quantum mechanics is just chaos, got it, thanks. But here's the thing. It's not chaos. It is the most precisely verified theory in the history of science. Quantum electrodynamics, the quantum theory of how light and matter interact, makes predictions accurate to 1 part in a trillion. That's like predicting the distance from New York to Los Angeles to within the width of a human hair. The math is immaculate. Reality is just deeply, personally weird. Now, entanglement. Because we haven't broken you enough yet. Here's the setup. Two particles interact in a way that links their quantum states together. Doesn't matter how. Maybe they're created together, maybe they collide. The point is, after the interaction, their states are correlated. Not like two coins that were minted together and happen to both be heads. Deeper than that. When they're entangled, neither particle has a definite state. They exist in a shared superposition. Together. And then you separate them. Send one to New York. Send one to Tokyo. And then you measure one. The moment you measure it, it collapses into a definite state. And the other one, instantly, simultaneously, regardless of the distance, collapses into the corresponding state. Not after a signal travels between them. Instantly. Faster than light could connect them. Einstein called this spooky action at a distance and hated it with his whole chest. He spent years trying to prove it was wrong. He thought it meant quantum mechanics was incomplete, that there had to be hidden variables, some underlying information that predetermined the outcome, and we just couldn't see it. In 1964, a physicist named John Bell figured out a way to test it. He designed an experiment that could tell the difference. Are the correlations pre-programmed, or are they genuinely quantum and instantaneous? His test, Bell's theorem, showed that if hidden variables existed, the correlations could only be so strong. Beyond a certain threshold, only actual quantum entanglement could explain the results. Every single experiment since then has crossed that threshold. Decisively. Entanglement is real. The correlations are real. The particles genuinely don't have definite states until measured, and the connection between them is genuinely instantaneous. No hidden information. No pre-programmed outcome. Just spooky, real, experimentally confirmed weirdness. And no, you can't use it to send information faster than light. We checked. The results you get are random. You can't control what state the particle collapses to, so you can't encode a message. The universe has excellent lawyers. It lets you have the weirdness, but closes every loophole you might try to exploit. Okay. Quantum computers. A regular computer runs on bits. Each bit is a 0 or a 1. Every calculation is a sequence of those zeros and ones, flipping back and forth. It's like a light switch. On or off. Period. A quantum computer runs on qubits. And a qubit, thanks to superposition, can be 0 and 1 at the same time until you measure it. Which means a quantum computer doesn't solve a problem by trying one answer, then another, then another. It can effectively explore multiple paths simultaneously because the qubit exists in a superposition of states. And thanks to entanglement, you can link qubits together so they influence each other in complex, coordinated ways that have no classical equivalent. This doesn't mean quantum computers are just faster. That's the most common misconception. They're not better at everything. They're better at specific types of problems, things like factoring huge numbers, simulating molecules, optimizing complex systems. A regular computer plays checkers better. A quantum computer breaks the encryption protecting your bank account. Different game entirely. We're still in the early days. Current quantum computers are noisy, fragile, and need to be kept colder than outer space to function. But the theoretical foundation is solid, and every year, the hardware gets better. So, back to the beginning. Reality is broken. The universe, at its smallest scale, doesn't have definite properties until observed. Particles take every possible path simultaneously. Two particles can be connected across any distance with no signal between them. The past might not be fixed. And somehow, impossibly, the math describing all of this predicts reality with mind-bending precision. The question physicists are still fighting about, the one that has never been resolved, not in 125 years of quantum mechanics, is this. Why does measurement collapse superposition? N. What actually happens when a quantum system decides to be one thing? N? Is there a wave function for the entire universe that never actually collapses, with every possible outcome happening in parallel realities we can never access? Or is there something about consciousness, about observation, that physically changes the universe? Or is the wave function not even real, just a mathematical tool that tells us probabilities, with nothing deeper beneath it? N. Nobody knows. The most successful theory in the history of human science is built on a foundation that no one fully understands. And every time someone thinks they've figured it out, the universe finds a new way to be weirder. Which honestly sounds like a pretty good reason to keep watching. So, do you think the universe is constantly splitting into infinite parallel realities every time a quantum measurement is made, or is our consciousness actually creating reality as we go? N! Leave your theory in the comments below, and make sure to subscribe if you haven't already.